Ion engines are great for spacecraft that can be patient. You can wait a long time to get from point A in the solar system to be from Earth to wherever you want to go. Because ion engines apply very, very little thrust. But, and they use very, very little fuel. But the fuel they do use lasts a long, long time. You can literally fire an ion engine for years, and it'll just keep going. You need to we'll need to bring some fuel, but it's very, very fuel efficient, which means you've got more room on your spacecraft for payload, for scientific payload. So it's a good deal, and you're going to see them used in space exploration more and more. So in this problem, we have an ion engine on a 400 kilogram spacecraft. And it delivers a 0.005 Newton thrust. How long must the thruster fire to change the velocity of the spacecraft by 1,000 meters per second? And it says use the impulse momentum theorem. So here's given. So here's our little spacecraft. And it's a little cube with little instruments on it. And it will definitely have solar panels on it. Yeah, you better draw the solar panels or you're going to lose credit. Okay, that was a joke. Now, and then it's got a little ion engine on it, and it just shoots. You can't actually see it. It's a kind of an ionizing blue color. And this little engine applies a thrust, and actually this will be the net force on the spacecraft, of 0.0050 newtons. And the spacecraft has a mass of 400 kilograms. And we want to change the velocity of the spacecraft by 1,000 meters per second. So that's delta V. We want to change the velocity by 1,000 meters per second. So if you see something like change the velocity, that's delta V. And I don't have to give you an initial velocity for that. Thank you. I just say, okay, the delta V is this. Okay, and what do we want to find? We want to find delta T, or just T. You can call it just T if you want. The time it takes, the time you would have to fire that engine. So let's solve. So the impulse momentum theorem says that the impulse on the object, that is the force I apply times time, and this should be the net force on the object, will be equal to the change in momentum of the object. Okay, fundamental law of nature right here. You push on something for a period of time, you're going to change its momentum. And so, well, this lets me solve for time right away, because all I have to do is go, okay, delta T is equal to delta P over the force. And what is my change in momentum? Well, that's my mass times my change in velocity over my force. And then, so now I'll plug in my values. And I'll do that down here just to fit on the screen better. The mass we said was 400 kilograms. Delta V was 1,000 newtons. And the force was, not newtons, I'm sorry, meters per second. Okay. And then I was looking at my units going, wait, that doesn't work. But yeah, 0.0050 newtons. And when you plug all that in, what'd you guys get? Let's see. It's going to be a big number, isn't it? So 400 times, well, 400,000, divided by 0.005, and you get 8.0. times 10 to the 7 seconds. Well, how long is that? I mean, that's 80 million seconds? Is that right? 80 million seconds. Dang. Well, I want to know how long that really is because I don't really have any idea. So I'm gonna do a unit conversion. You didn't have to. If you stopped here, you're fine. But so let's see. There's 3,600 seconds in an hour. Let's do this in days. And then there are 24 hours in one day. So that goes away. So I'm going to divide this by 3,600. And then I'm going to divide that by 24. And I get 925 days, or 926 days. Wow. Let's divide that by 365. And you get about 2.5 years. You have to fire that engine for 2.5 years. So that's a long time. So if you have an ion engine, and this isn't, by the way, a very big spacecraft. Now, actually, I think on the Dawn spacecraft, they said they had 3 ion engines on it, so it's 3 times. So take 1/3 the amount on it. But I think the spacecraft's a little bigger. Might be interesting to look that up. But ion engines are probably not a good way to go for for sending humans to Mars or wherever, because who wants to wait that long? But if you're a robot, you don't care. Robots don't care. They don't have feelings. We may, give them names, and we may, treat them and talk to them. But I know kids on the robotics team do, but they really don't have any feelings at all. They're just inanimate objects. And so we can send them out there for however long we want. And, if you're a scientist, it might be kind of frustrating to wait 2.5 years for your spacecraft to accelerate to the point you can get to where you want to go. But that's okay. Scientists don't make very much money. They can wait. Obviously, NASA and other groups are investigating new ion engines that will be able to give us much more thrust for the same miserly fuel consumption. So maybe someday, like in Star Trek, will come true. We'll have ion engines that can push humans around. But that day isn't here yet. But it's probably coming. Anyway. That is all.